Hi, welcome to another video in this series of problems on linear transformation. If you're new to this channel, my name is Dr. Abdul Wahab Animoku, and I'm a college maths instructor. In today's video, we are going to look at how to find the rank of a linear transformation. So let's just get right into it. Okay. So in this problem, we have a linear transformation R from P3R to P3R. So what does this mean? So first of all, let's break this thing down. What does P3R mean? It means we have a space of polynomial of at most degree 3. So what it means is, so this contains, so P3R, so it contains the set of all, so the vectors in this particular space would be the vectors, just a polynomial set that would contain anything from polynomial of degree 1 or even polynomial of degree 0 to polynomial of degree 2 to degree 3. So all of this are the vectors we are expecting from this particular vector space. So if you're familiar with linear transformation, you would know that polynomial space with real coefficients are vector spaces, right? So this is a vector space from P3R to the same vector space. So we call this an endomorphism. So when you have a transformation from one vector space to the same vector space, we call it an endomorphism. Right. So now we want to try to find the rank of this endomorphism. So how do we do that? Now, this is how the transformation operates. It takes a vector, which is a polynomial, and then it finds you the derivative of x times that polynomial. So let's just take an example. So what it means is, let's say, remember, this P of x is coming from this vector space, right? So let's say we take P of x. Let's look at one of the examples that we have here before, this polynomial of degree 3. Okay, let's say we take this. Now, what this transformation does to this vector would be, so let's have this. So this, according to the transformation, is going to take the derivative d dx of when we multiply x with this vector. This is what it does. So that is derivative of 3x raised to the power 4 plus 2x squared minus x, right? And what would this give us? Derivative of this, as you know, derivative of polynomial is just when we multiply the constant with the power, then we reduce the power by 1. So that would be 3 times 4, that is 12, x raised to the power 4 minus 1, which is 3. And then the next plus the next one, which will be 2 times 2, which is 4, x raised to the power 1. And then finally, derivative of x is just going to be minus, just going to be 1, right? Because think about it, the power here is 1. So 1 times 1 here, that's still 1, x raised to the power 1 minus 1, which is just x raised to the power 0, which gives 1. So this would be the derivative that we have, right? So this is what this transformation does. It takes, as you can see, this vector is also a vector in what? P3R. Right? It's also a polynomial of at most degree 3. So this is what this transformation does. Now we're trying to find the rank of this. How do we do that? So the first step in this process is to first of all find the matrix of transformation relative to standard basis, right? So if we can find the matrix of transformation, that will now allow us to understand how to find the rank of such transformation, right? Because the matrix tells us everything we need to know about the transformation. Okay, so let's just get right into it, right? So the first thing is we need to find the matrix of transformation relative to standard basis for P3R. For both the domain and the range of this transformation. And what is that matrix of And what is the standard basis? So standard basis for P3R is just this vector, this set, basically, x cube. So this is the standard basis. So let's call this E. Okay. Now, relative to this, we are going to find the matrix of transformation. So the first step in the process is we need to find R of each of this vector. This idea we've mentioned in the previous video. Please, if you have not watched those videos, the link will be in the description. Make sure you go ahead and watch those 2 videos first. In fact, you can watch those videos after this particular one, right? So what we do first is we find the transformation of these vectors in the basis. So R of 1 would just be basically what the derivative of x times 1, right? So that's just going to be 1. The derivative, the second one will be the derivative of what? X. Remember, in the transformation, you have x times p of x. So that will going to be x times x, right? So derivative of x squared, that would give us 2x. And the next one, we're going to have d dx of what? X multiplied by x squared. So that will be derivative of x cubed, which is 3x squared. And finally, the derivative of x times x cubed, which is x raised to the power 4, which is 4x cubed. Now, what we do from here is we try to write this as a linear combination of the vectors in the standard basis, right, for the range of this transformation, right? So in this case, we're going to write it as what? So this will be the entry of a matrix that will give us the matrix of transformation. So A11 times the first vector in this standard basis plus A21, the second vector, plus A31, the third vector, plus, so let me just make a small space here. I think we can all see this, plus A41 x cubed. So let's quickly do the rest. So this is A22 times x, A32 times x squared, A42 times x cubed. And the next one, A13 times 1, A23 times x, A33 times x squared, then A43 times what? X cubed. And finally, we have A14 times 1, A24 times x, A34 times x squared, A44 times x cubed. Okay. Now looking at this, all we need to do now is to compare the coefficients. So compare the left-hand side with the right-hand side. As you can see, in the left-hand side here, we only have 1, right? Which means the coefficient of x, x squared, and x cubed are all 0, right? So we can get that basically. So let's start forming our matrix of transformation. So for the first set, we know that what? To get 1, we just need A11 to be 1, and then the rest of the coefficients must be 0. So therefore, A11 would fill this space, A21 would be 0, A31 would be 0, A41 would be 0. Okay. Now let's move to the second row. Now in the second row, we can see that what? Only coefficient of x is 2. The rest of the coefficients have to be 0. So therefore, the first coefficient A12 will be 0, A22 has to be 2, A32 is 0, A40 is 0. So we do the same thing for the rest. So in this case, this is what we have, and the last one, this is what we have, right? Because the coefficient of x cubed is 4, which means A44 is 4, and the rest of the coefficients would be 0. Okay. Now, this is the matrix of transformation. Now, what do we mean by the rank? The rank of a transformation. So it basically means when we get the matrix of that transformation, the simplest basis that we could use is the standard basis. You could use any other basis for this transformation and your answer will still be correct, okay? But this is the simplest matrix that we can get. And as you can see, it's a diagonal matrix. Oh, this tells us something. Basically, this A1, A1, 2, 3, 4 are the eigenvalues. This is something else that we can get from this. Are the eigenvalues of the transformation. And the eigenvectors vectors in this case would be the standard basis. How cool is this? So these are the eigenvalues 1, 2, 3, 4 relative to this eigenvectors. As you can see, we have a diagonal matrix, so that tells us about the eigenvalues and the eigenvectors of that transformation. But anyways, let's not digress. Let's now talk about how we find the rank of this matrix. So what does it mean to find the rank of any matrix? It basically means the number of what? Linearly independent row or column vectors. So, a simple way to do this is just to observe that what another way to think about this is if we reduce this to a row reduced echelon matrix, then we kind of use this row reduced echelon matrix to determine the rank of the matrix. So when you look at A, you see that what when this is already in a row reduced form. As you can see, the first entry is 1, and then subsequently we can reduce each of them, divide this by 2, divide this by 3, divide this by 4, and that will give us a very simple matrix, which is a row reduced form. So basically, if I want to reduce this even further, where each entry has 1 as its where each if I look at each row, it must have 1 starting each we must have 1 starting each row. So if we look at that, then we can see that what we can reduce this by dividing row 2 by 2, dividing row 3 by 3, and dividing row 4 by 4. When I do this, I'll basically have the identity matrix, right? So I can do this. Now that I have this, if you look at this, these are all linearly independent. As you can see in each row, so this is what we mean by row reduced echelon form. As you can see, from if you check each column, you can see that what each starting point is to the right of the previous one, and we end the matrix at the last entry of this matrix. So basically, all the four column vectors or row vectors are linearly independent. So therefore, the rank of A is what 4. So that answers the problem. But there's another way to look at this, which is basically what to check the number of linearly independent rows or columns. So if you don't want to go into the route of reducing this matrix to row echelon form, you could also solve it this way. So what does it mean for the vectors to be linearly independent? It means if I do this. So let's use the row vectors. So linear combination of these vectors. So it means linear combination of these vectors and the last one is 0, 0, 0, 4 must be equal to the 0 vector, right? So what does this mean? Now, if you're able to solve this for A, so we need to solve this for A, B, C, D. Now, if you're able to get a trivial solution that A must be equal to B, must be equal to C, must be equal to D, must be equal to 0, if you're able to get that condition on A, B, C, D, then it means these vectors are linearly independent, right? So this is basically what we need to do. So when we do this, we see that what A, check the first component, A times 1 plus B times 0 plus C times 0 plus D times 0. That will just give us A, and that must be equal to 0. Remember, in the right-hand side, we have the 0 vector, which is right on the right-hand side. So the first component must be equal to 0. The same thing for the second component, A times 0, B times 2. So I have 2B plus C times 0 plus D times 0 must be equal to 0, which means B must also be equal to 0. I will do the same thing for the third component. It means 3C must be equal to 0, means C is 0, and then 4D must be equal to 0, which means D is equal to 0. So these are the two ways. So therefore, it means that what the four row vectors are linearly independent. Hence, the rank of the matrix, the rank of A must be equal to 4. So this is the answer to the problem, right? You can use both ways to solve this problem. Now, one caveat, one more thing that you should note is, say we try this and the 4 vectors are not linearly independent. That means the rank is not 4. So we check for the first. So we leave out one of the vectors and check for the first 3. Right now, if we check again and these 3 are not linearly independent, that means we need to check only 2 of them, right? This is how you reduce the vectors until you get linearly independent set of vectors. All right, so so thank you very much for staying to the end of this video. I will see you in the next one, right? Don't forget to like, comment, and subscribe to the channel so that we can support this channel to grow and to help other students to be able to see these videos as well. All right. Have a nice day, guys.